Hi, and welcome back to Hacker101. In this session, we're diving headfirst into understanding and hacking native code. This is an extremely advanced topic, but by the time you're done with this video, you'll have a great head start on the subject. Before we actually talk about the details here, let's talk about what native code actually means in this context. The term is used in a number of different ways, so for the purposes of this discussion, native code is anything actually compiled to machine code. This means most applications you download, most software running on game consoles, most firmware, and more. Basically, if the binary was originally compiled from C, C++, Rust, or other languages typically compiled to machine code, that's what we're talking about here. This is an area you can spend decades learning and still not be an expert on even half the subjects at play here. So for this session, we're not going to try to go too deep on any specific point, but give background information and broad overviews of the concepts. Once you get through this, you're going to be left with many more questions than you had going in. We're going to be linking to a ton of useful resources, so you can answer those questions and dive deeply into the areas that particularly interest you. If there's one thing I want you to take away from this lesson, it's this. Code is data is code. There's simply no difference between the two. Arbitrary data can be executed as code, and code can be analyzed and manipulated just like you would do for any other data. Personally, this blew my mind when I first realized it. There is no magic formula that makes code code. It's just data that you're telling the CPU to execute. Do you want to see what the code is doing? Take it apart. Do you want to change the way something works? Open it in a hex editor and tamper with it to your heart's content. This, to me, is the fundamental realization that underpins all of native code hacking. Now that we've covered some of the background bits, let's talk about how a computer really works. You're not going to have a thorough understanding of every single one of these areas, but the more fundamental knowledge you have, the more creative you can be with your discovery and exploitation of bugs. One last note, I'm going to be talking very generally here rather than digging into the details of any one OS or architecture, and I'm simplifying some bits, but remember, this is just a starting point. First, let's talk about registers. These are small areas of memory located within the CPU itself where you can store and manipulate data. Since the CPU doesn't have to go talk to external memory, reading from and writing to registers is effectively instant. This is where most data for operations will be located. In fact, in most architectures, many operations can only be executed in the context of registers, like reading or writing memory or doing arithmetic. When I say in the context of registers, I mean that you may have an operation to read from somewhere in memory and put that value in a register or add two registers together, but you may not be able to read from somewhere in memory and store it somewhere else in memory or add a value directly to some value in memory. Most everything you do will have some pit stop in a register. Depending on the architecture in play, you may have as few as 6 general purpose registers, ones where you can perform any operation rather than special registers that can only be used for specific things, or as many as 32 or more. Given this, a lot of code is really just going to be moving data in and out of registers as efficiently as possible. If you're writing something to memory, reading it back, performing an operation, writing it back, and repeating, you're just wasting CPU cycles. So compiler developers spend a lot of time just optimizing those activities. Since register space is so limited and accessing long-term storage like hard drives is so slow, memory is where most of the state of an application will be stored. Whether it's objects that are created, loaded images, or anything else, memory is likely where it'll be. On modern systems, it's important to split the discussion of memory into two parts. Physical memory, which is the actual RAM on the system, and virtual memory, which is an abstraction that allows us to access that physical memory. Physical memory is usually addressed from 0, so if you have 64 megs of RAM, for example, the lowest physical address will be 0, and the highest will be 0x3FFFFFF. Any physical address in that region will correspond to a single byte of actual memory on the system. All that said, applications running on a modern OS will never directly access physical memory. If I can read and write physical memory directly, I can snoop on or tamper with any other application, including those of other users or system processes. Virtual memory is what we use to access physical memory in a safe way, separating processes from each other and also allowing us to share code or data between processes quickly and easily. The heart of virtual memory is the page table, which splits the address space of a process into individual pages, usually 4 kilobytes each on a 32-bit system and 4 kilobytes or 2 megabytes on a 64-bit system. Each of these pages is either unmapped, meaning it doesn't point anywhere and any attempt to read or write that address will cause a crash, or it will point to some physical memory address. Each entry in the page table also specifies the permissions available for that page, which is some combination of read, write, and execute typically. Here's a diagram that shows the basic structure of how a virtual address space might map to some physical memory. The text segment is what code is typically called, while data is exactly what it sounds like. Each page in those regions would have its own entry, pointing into physical memory. The stack is one of the most important concepts in native code, as it's where all the local variables for a function are located. Contrary to what might seem like the obvious choice, the stack is said to grow down. What that means is that if you have a stack that's allocated at 0x10000 and goes up to 0x20000, the first value would actually be written at or around 0x1FFF8 and the last value at 0x10000. When you call a function, or subroutine as it's often called in assembly, you create a new stack frame. In essence, you store the stack pointer, the current address for the top of the stack, then subtract from that to give yourself space where you store any local variables that are required for the current function. Once that function is over, you restore the saved stack pointer, effectively giving back the space you took on the stack. So if you're looking at the stack pointer will be pointing at the top of the stack, which is the current function that's executing. If you keep looking upwards in memory, you'll be going backwards through the call stack, all the way until the first function that kicked it all off. By the way, that first function is often called the entry point, or EP. Endianness is a property of the CPU, which determines the order in which bytes of values are stored. This is needed because memory is indexed in bytes, 8-bit units, and most values are larger than this. As such, we need to split the value into some sequence of bytes. Endianness decides the order. In little endian systems, values are stored with the least significant byte first in memory. That is, if you have the value 0x01AB23CD, this would actually be stored as 4 bytes in the order CD23AB01. In big endian, it's the exact opposite, with the most significant byte stored first. That value would end up being 01AB23CD. While big endian systems certainly still exist, especially in embedded hardware, they're much less common than little endian systems these days. If you're on any x86, x64, or ARM system, it's almost certainly going to be little endian, and that covers the vast majority of the systems you'll interact with. Without going into too much detail, since this part is intimately tied to a given architecture, an instruction is the basic unit of machine code. Each instruction will typically execute one and only one operation, though there are exceptions. Common operations for which you'll see instructions: add 2 registers together and store it in a third register, compare the value in a register to some number, jump to another instruction, possibly conditionally based on the results of a comparison. Generally speaking, picking up the individual instructions for a given architecture is pretty straightforward, especially once you've learned 1 or 2 others. As such, this is mostly just a matter of spending time reading code and working through what it does. The program counter, PC, or instruction pointer, IP, is a special register that tells the CPU which instruction should be executed next. Typically speaking, you can't directly write to this, and on some systems you can't even directly read it. As such, special instructions exist to set or get this value. For instance, a jump is really just an instruction that sets the PC to some new value. Calls are a special type of jump instruction which, before changing the program counter, first stores the address of the current next instruction somewhere, often to the stack or to a specific register. This is how a subroutine or function gets called. When it's done executing that subroutine, that saved return address is used to tell the CPU where to continue execution. Often there's a specific instruction called ret or return which automatically handles this part for you. Syscalls are how an application talks to the kernel, the heart of the operating system, in order to perform operations like reading or writing files, sending or receiving data on the network, launching other applications, and pretty much any other interaction with other parts of the system. The details on how syscalls work are highly OS specific, but this is a term you'll see a lot. Finally, let's talk about shared libraries. While you could build an application by including every single piece of code you need to use inside that one single binary, which is called static linking, this is wasteful since most applications will share a lot of code with other programs. To alleviate this, we use dynamic linking, where the application is able to call functions in other binaries called shared libraries. If you've ever wondered what a DLL is on Windows, or a .so file on Linux, or a dilib file on Mac, that's them. When a program gets loaded into memory by the kernel, it loads the required shared libraries as well and sets up some structures to allow them to be called. Additionally, it's possible for shared libraries to be loaded at runtime by a program, which is often how plugins are implemented. The program will load a shared library and then call specific functions inside it to initialize the plugin and give it access to the data it needs. There, you made it through the architecture crash course. I know that was a lot of information all at once, so take a nice deep breath and then let's talk about tools. First up are disassemblers, which take machine code and convert it to a readable form, which is assembly code. There are two types of disassemblers you'll come across: interactive and non-interactive. Interactive disassemblers are typically GUI based and allow you to browse through code, annotate it to give things names, etc. Non-interactive diassemblers simply take in a binary and give you an assembly file back. This is also called dead listing, since it's just a static text file. IDA Pro is by far the gold standard for interactive disassemblers. It carries an exceptionally high price tag, sometimes into 5 figures with plugins, but it's widely considered the best tool for the job. Hopper is a personal favorite of mine, which is particularly great at dealing with Mac and iOS binaries. It's also much less expensive than IDA. A newcomer to the area is Ghidra, which was released as an open source project by the NSA. It's directly competing with IDA, and while it's still new and relatively buggy, it's pretty great and completely free. I could be wrong, but I think we'll see a whole lot of folks moving from IDA to Ghidra over the next couple years. There are literally hundreds of non-interactive disassemblers, but a few notable ones include OBJDump, which comes with GNU bin utils and thus is already included on most Unix-like systems, ODA, which is a really nice online disassembler, which can be really useful for tiny snippets of machine code, and Radair2. Radair2 is actually a huge reverse engineering framework, including some interactive GUIs, but the learning curve is very steep. The non-interactive tools, at least, are extremely nice, so once you learn it, you're going to be very efficient. Next, we have decompilers. Rather than taking machine code to assembly code, these attempt to translate machine code back to something like C code. This can be really great for gaining an understanding quickly, but it can also be very buggy and hide important details, like the layout of the stack. IDA has a set of decompiler plugins called Hexrays, each of which covers one specific architecture and costs several $1,000s each. However, both Hopper and Ghidra include capable decompilers as well now. They haven't quite hit Hexray's level, but they're getting there and are perfectly suitable for most purposes. Debuggers allow you to actually attach to a program and see or manipulate its state at runtime. You can see the state of registers, memory including the stack, and more. The GDB and LLDB tools are great debuggers on Unix-like systems. WinDBG is a great debugger for Windows, and most interactive disassemblers also include their own debuggers that integrate nicely with the GUI. Hex Editors are a more general tool, but they are incredibly important for this kind of hacking. They allow you to open the binary and see all of its contents, easily enabling you to patch machine code to change functionality or manipulate data at will. I personally recommend OXED on Mac and HXD on Windows, but there are hundreds to choose from. It's really just down to personal preference, as there is no real gold standard here. Finally, assemblers are, as the name indicates, the opposite of disassemblers. They take an assembly code and give you machine code. For the purposes of hacking native code, this typically means just assembling a couple instructions so you can patch them into an existing app. There's an online assembler by Shellstorm that I personally use for this, as it allows you to assemble code for a number of architectures right on the web. No need to install a bunch of other tools. Now let's talk about some types of bugs that can pop up in native code. Saying that this list isn't comprehensive would be a pretty severe understatement, but these are some of the most common and important bug classes. You may hear these referred to as memory corruption bugs, as that's really the root of it. You cause memory to be corrupted into the correct state for your exploit to function. Buffer overflows are probably the most well-known of these bugs. These happen when data is being written to some chunk of memory where the data is larger than the target region. If you have some 8-byte buffer allocated on the stack and write 18 bytes of data into it, you're really writing 8 bytes into that buffer and then 8 bytes into something else entirely. In the old days, you would just seek to overwrite the return address on the stack. Then when the function returned, the attacker would have control over the address that it went to next. We'll talk about why that isn't generally very possible nowadays, but buffer overflows, specifically targeting other local variables on the stack typically, are still really important and affect lots of software. Let's look at an example in some pseudo C code. If you imagine this happening inside a function, this creates an array of 4 8-bit values, bytes in other words, and then a 32-bit unsigned integer that's initialized to 0. Because of the fact that the variable value comes after the buffer, it's likely that it will be placed directly after it on the stack. That's important for the next step. We use the strcopy function, which copies a string into the specified buffer, to copy test AAAA into the buffer. Note that that's 8 bytes being written into a 4-byte buffer. Clearly, this isn't going to be good. If we then print out a hex representation of value, we don't get 0 like we expect. We get 0x41414141. Why? Well, it's because we wrote past the end of the buffer, right over the value variable. AAAA, an ASCII hex representation, the typical way we'd represent text in numerical form, is 0x41414141. As a slight tangent, you'll almost always see people use AAAA to test buffer overflows and such, since that value sticks out so nicely. Next, let's talk about out-of-bounds writes. These are kind of like buffer overflows, except that it's about controlling the start point of the write. That is, when you overflow a buffer, you're still starting at the beginning of that buffer, or some fixed offset inside it. But here, you're hijacking the offset to write things where you need to put the data. With an out-of-bounds write, you may or may not be able to control the value that's written, but as long as you have a rough idea of what's going to be written, there's almost always some clever way to harness this. In this example, we have a vulnerable function that takes in an index as a parameter. Inside it, we have an array of 16 32-bit integers, then another 32-bit integer that we initialize to 0. We write oxdeadbeef to the array index specified in the function call, then print out a hex representation of the value variable. If we called this value with anything in the range of 0 to 15, the good indices of this array, the value would still be 0. But because we're writing to whatever value is just after the end of the array, we end up overwriting the value variable, and we see that the value is oxdeadbeef as expected. As with buffer overflows, you could also go just past it and end up overwriting the return address. If you do have control over the value, unlike this scenario, this could directly allow you to get control over the program counter, and you're nearly done with your exploit at that point. Finally, we have use after free. This is most likely the most impactful memory corruption bug today, and it's also the hardest to find and prevent. In essence, this bug occurs when you have a reference to some area of memory, then that memory gets freed and written over with newly allocated data. If you still use that reference, generally known as a stale pointer, then you're going to be performing actions on data that you don't at all expect. The reason that this is so dangerous is that, depending on what exactly the code is doing with that stale pointer, this could lead to anything from an information leak, like getting memory addresses, arbitrary writes anywhere in memory, or even direct code execution. Often these bugs occur due to a huge chain of weird events, and they pop up in browsers all the time because of the complexity of their code. What's worse is that these bugs often allow you to bypass the major protection mechanisms that have been developed, making them seriously dangerous. Speaking of protections, let's talk a little bit about how compiler developers, operating systems, and CPU manufacturers are fighting back against exploit developers. First up are stack canaries, which are really cool to me. Because the return address for a function is just sitting on the stack, a buffer overflow can easily overwrite it with some arbitrary value, as we discussed. So stack canaries work by creating some random value at the start of execution, then putting that just between the local variables of a function and the return address. Then, just before the function returns, it checks the value on the stack against that global random value. If it doesn't match, the program exits. If you use a buffer overflow in the traditional way, you'd need to have some way of getting that global random value, otherwise the program will just die. This isn't a perfect defense by any means, but it prevents at least naive buffer overflow exploits from succeeding. Consider the example of the out-of-bounds write from before though. With that, you're able to skip right over the stack canary and just write over the return address. Now we have the NX bit. In many systems, memory pages only have read and write permissions. Anything readable is also executable. So if you can write some code onto the stack, for instance, then executing it is as simple as getting program counter control and pointing it at the right place on the stack. The NX bit, implemented in a bunch of different ways by different processor manufacturers and architectures, fixes this by adding an explicit flag for a page being executable. Now you need to be able to write your code into somewhere that's both writable and executable, or you can't execute any code directly. Which brings us right into our next protection, W XOR X. Many applications need to be able to write new code to memory during runtime. A good example is the browser compiling JavaScript to machine code for performance reasons. If you simply allocate new pages that are both writable and executable, an attacker just needs to find a way to write to those pages and then jump to that code. It's a hurdle, sure, but totally doable. W XOR X means write or execute, but not both. Under W XOR X, the OS will prevent you from marking pages as both writable and executable to prevent exactly this kind of naive attack. So in the case of that JIT compiler for JavaScript from before, the compiler would allocate some new pages as normal writable memory, then switch it into being just readable and executable. This is more of a hassle for the compiler devs, but now attacker choices are much more limited. Finally, let's talk about ASLR, or Address Space Layout Randomization. Normally, a binary has a specific base address where it gets loaded, and the stack is also at a fixed address. So an exploit just needs to be written to use those specific known addresses. With ASLR though, each binary that's loaded gets a randomized base address, greatly increasing exploit complexity. You can't just use a single payload and expect it to work consistently. On a 32-bit system, there may be only 10 to 16 bits of randomness, which means 1024 to 65 536 possible base addresses, well within the range of guessability. However, on 64-bit systems, this might be as high as 24 bits of randomness, or about 16 million possible base addresses. That makes it a little bit harder, to put it mildly. Well, this session would be a bit of a bummer if we just stopped at describing the protections. If you've made it this far, it's because you want to build your own exploits, so let's talk about how to get around these clever mechanisms. First and foremost, JavaScript is your friend. I really can't stress this enough. If you have a choice of multiple entry points, always choose the browser or something else with a JS engine. There's always a way in. ASLR alone makes this one a no-brainer, because your exploit is almost certainly going to need to adapt to the situation in the process. The easiest way to do that is to have some kind of code running in there already, then adapt your exploit to the base addresses and such that you see. Not only that, but browsers and JS engines in general are just huge, complex pieces of software. Spend a few days looking through the commits for any JS engine, and you'll become very paranoid about what you do on the web. In order to get around ASLR, you really only have two options: guess addresses or know the addresses. If you are targeting some service that immediately restarts when it crashes, and it's only using 12 bits of randomness or some such, you can honestly just choose a specific address and keep throwing the exploit at it until it fires. That's the guess approach. If it takes a second per attempt, that'd take an average of about half an hour to work. Not terrible by any means, depending on the scenario. However, a much more precise and fun, in my opinion, method is to just use information leaks to get your bearings. A great example of this would be a bug in a JS engine that lets you get the address of a given built-in function. If you can do that, you can figure out what the offset of that function is inside the binary, then just subtract that from the address you get to give you the randomized base address. From there, you can tweak your exploit automatically to make use of that and call whatever functions you need to use. Heap spraying is another technique that has become more and more valuable over time. If you don't know exactly where your exploit needs to be, or you can't get it there explicitly, this is where heap spraying comes in. Instead of putting one copy of your exploit in a specific location, you create thousands or millions of copies of it. The more of them there are in the memory, the higher the likelihood that your exploit will be in the right place at the right time and succeed. This won't always work, but heap sprays can be extremely effective. There's also a related technique called heap feng shui, where you make a bunch of really precisely sized allocations with the goal of getting your exploit exactly where you want it. Super interesting stuff. The final technique we'll talk about is ROP, or return-oriented programming. This is a super brief explanation of an extremely complicated subject, but hopefully this will give you enough to be interested in learning more. ROP came about in response to how difficult it became to actually get your code in place to be executed. Between NX and WX or X, it's become more and more difficult. So instead of trying to put your own code in place, ROP seeks to build a chain of a bunch of small chunks of existing code from the process to accomplish whatever your goal is. Your code ends up being made of a bunch of separate gadgets, which are each 1 to 5 instructions long, typically, and then end with a return instruction. What makes it return-oriented programming is that you do what's called a stack pivot, changing the stack pointer to point to some other part of memory where you've constructed an alternate stack. This new stack consists of a bunch of return addresses and relevant bits of data, such that when control flows into each of these gadgets, it basically performs any operation you can imagine. In fact, it's often possible to use ROP techniques to build a Turing-complete environment. That means that any operation you could perform in a normal programming language can be performed 100% from these extremely complex ROP chains. As I said earlier, this session was going to dump a lot of new info on you, but I hope that you're coming away from this with a burning interest to learn more about native hacking. We've put a ton of resources on Hacker101 to help you learn about this from every direction, so please take a look at that. Also, if you haven't done so already, please consider giving the video a like and subscribing to our channel for more content. As always, thanks for watching and happy breaking.